இதா இருக்குமா? Hi, Madhukar.
Yeah, hi, sir.
Can you hear me?
Yeah, I can hear you. I'll just get the...
You're also coming through clearly.
Okay.
We're going to have to wait for...
Yeah, sure.
Okay. But today, because we are usually earlier than the thing. So unlike, I'm taking the later shuttle today.
Oh, okay.
Okay. So if
you can still take the 5 o'clock thing,
huh?
no? You should be able to take the 5 o'clock.
No. I know what will happen at 5 o'clock. Okay, because these people, they show up only, around 3:40. They just lazily come around here. So I've been noticing, on an average, I'm not able to start at 3:30. I mean, it's usually like 3:40 or so.
Yeah.
I've never been able to start the class on time.
Yeah, I think this is something that I face here in Delhi.
And it kind of matters now. So I'm going to take liberty today to see. Maybe they all, because I record and then upload it, maybe they think that they don't need to show up.
Yeah, either that, or I think I also start my classes a little late.
Few minutes late. This is Romit. Okay, so there are some. Yeah, I mean, I guess he is. I'm seeing a strange face today. It's been a long time since I saw you. So what's your name? Anurag. You spell it with a J. But how is it pronounced? Oh, Anuraj, not Anurag. Oh, okay. Anuraj. Okay. So, yeah, we'll wait for a couple of more minutes. And there are some folks last time. I mean, mostly the folks that were here last time were all CS, I think. You're CS? No. You're DS. Okay, so I don't know if you got it. I mean, at least the CS folks who were here, and last time there were 4 people here and 2 people on the thing. There were still 4 people missing that are registered in the class. They were all from CS, so they felt that generally they see that you could go faster. Okay, that's the feedback that I've also got. But then I also get some feedback from some people. I don't know, Anuraj, did you go through the yeah, but how did you find last lecture? Was it at in terms of the pace? It was good for you. See, that's the thing. There are some people who have not had a lot of logic. You know, for them, we may not have to go. The pace which you went was okay. So we have 2 sets of audience. So I think we cannot. We'll have to bear that in mind. Okay. Okay. So I think I will start recording, and you can start now. Yeah. Just a minute.
This meeting is being recorded.
Oh, I shouldn't be sharing. Okay. So you can share. Okay. So before we start, a couple of things. I'm sure you'll start. I mean, I'm going to ask if any of you did you get to attempt at the class exercise problems? Huh? So Madhukar, you will. I'll request you to start with that.
Yeah. Sure. So
Discussion.
let me connect and share my screen. So.
You could. I mean, since the people seem to have attempted it, you could probably ask them what their answers are like, and then you can motivate that. That is one. Before I let Madhukar start, I've already assigned, I've made tentative assignment of the papers, and I've also assigned mentors for you, okay? And so far, I don't think anybody, I don't know if you have contacted, any of you have contacted your mentors. The first thing is, what I wanted you to do is to quickly go through abstract and introduction and make sure that you are comfortable. You should have already done that. Okay, I told you last time, if you did not do it, you're stuck with those papers. Okay, but being a very kind person that I am, that I will still that's a self congratulatory thing. You will know for sure whether I'm a kind person or not when you see the grades at the end of the thing. No, but I have a reputation for being a kind person. Okay. Yeah, so you could still have a chance to do it, but I think this has to be done this week, because I have to start scheduling the presentations. And before the presentation, you have to have read the paper, selected the paper, read the paper, discussed with, I expect you to discuss it with the assigned mentor to make sure that, you have understood the paper well enough to be able to present it, because making a presentation will require you to understand it even deeper. It's not like, that's the way it is, okay? So when you read something, you might have understood it, but when you try to present it, you will have to have an even deeper understanding. I mean, I say if you try to write a summary, a detailed summary of it, then you will have to get an even deeper understanding, because you have to put things in writing. So while we are not asking you to write a description of, summarize the paper, we expect you to make a presentation. Now that means that you should first make sure that you discuss with your mentor and demonstrate, make sure that you have clarified all your doubts, and you demonstrate to that person that you have, to your mentor, that you have understood it well enough, okay? And then you will have to make the slides, okay? All that will require at least 2 weeks before your presentation, 2 weeks. Okay, this will require 2 weeks. I'm saying if you want to make a decent presentation, and I want you to put that, and this is for 40% of your grade weight, okay? And I think that's how I have it. I mean, from what I can remember. So I want you to take it seriously and then get started as quickly as possible. So I will try to, and pedagogically, there is a certain order in which I might want to schedule those presentations, but I'm not sure if I'll be able to do based on your own time schedule and things like that. But I will try to accommodate and then try to be a little bit flexible there. But then we'll have to pretty soon decide, because it's
Recording
it is
in progress.
at that point. And
Just one
yeah,
second.
we'll have one more week, maybe 3 lectures at okay. Is muted. Oh, he has 2 things.
Yeah, no. Is that fine now? Is it
There
better?
was some feedback that I noticed here. So what I'm saying is, pretty much, okay, by the end of next week, I want to, for each of you to have decided, on the paper that you've assigned, that you've been assigned, that you're going with it, and had one meeting with your mentor, okay? So that's what I want. So now off to you, Madhukar.
Yeah, so have they started, because I think I was approached by only one of the students regarding one of the papers.
No, I thought, well, take a look at that.
So can you also make me a co-host in the other one so that I can share my screen?
You have actually 4 people, okay?
Yeah, but I was approached by only one of them. So I believe the others are already reading their papers.
Approached by?
I was approached by Guhan.
Okay. Guhan is close to where you are, okay? So the people, Anuraj, Sulagna, Guhan, and Sainthan.
Yeah, so I was not approached by the other 3. So I believe that they are reading their papers and they're not stuck anywhere. But it's a good idea to meet anyway. Even if you're not stuck, it's a good idea.
I want them to get started. It's already too late. I mean, I preferably by next Wednesday or Thursday, next Thursday's class, I want this thing to have been finalized and the schedule be decided, so that you will have the people that are I will try to schedule some people who already, I know one or two, like Arpan, for example, you already started reading it, okay? Although you're not the first choice for me because it's on reinforcement learning, which we have not covered at all, okay? But nonetheless, we'll talk about the schedule, by Thursday. So if between now and next Thursday, that is within a week, you would have decided, finalized the paper, and have had one session with your advisor, then that will be good for to decide on the thing. Sulagna is here. We were just talking about Sulagna, that I wanted by next Thursday for you to, for everyone to have been comfortable with the paper that you have assigned, which will require that you will have to at least get a quick read of your thing. So next Thursday, okay, the sooner the better, okay. So and have had one session with your mentor, which in your case is Madhukar, and yeah, so that's what I was talking about. Yeah, okay.
Yeah. So, sir, can you make me a co-host in the other one also?
In the other one you are.
Yeah.
Sure.
Yeah.
Okay.
Yeah. I'm sorry about this.
Oh, Diganta is here as well.
Yeah. The answer is.
Yeah, you're co-host on both of them.
Yeah.
You can share.
Okay. Can you see my screen?
Yeah, I will. I think from my end, I can make it bigger.
Okay. So we wanted to start with the questions, right?
Yeah. Can you get rid of that? But you need that palette. I mean, that.
Yeah, I don't know. It should be
why can't you make full screen? You don't like it, is it?
No, I don't know how to make full screen. I like it, but I don't know how to.
Okay. That's okay? Yeah. That's the best. I mean, usually there is, the full screen, usually you get, either you have to go to slideshow mode or full screen mode. Usually there is something like that.
Correct. So
when you
this
do
is already...
Under view, you have full screen mode.
So this is already full screen according to the...
Okay.
The application. Yeah. So I don't know, but...
Let's go ahead. We have already spent 15 minutes.
Yeah. Sure. So should we start with the questions, or should I go ahead and complete?
That's what any questions based on whether you were here in person last time, or if there are no questions, I think you should ask them questions.
Yeah.
What was the answer for your first thing? I mean, first of all, can you flash that?
Correct. Yeah.
By email.
Yeah. So this is... Is this visible? Can you guys see it?
Yeah, I think so.
Okay. So here are some questions. I'm not sure if you looked at these questions or not, but okay. So for instance, the first one says that, if you assume that, there is an over approximation which has been denoted by n hat, and this is you know that this is a sound abstraction, right? Which means that, for a property P, if n hat satisfies P, then n also satisfies P, right? So if basically if P holds in n hat, then P also holds in n. Okay. Now, okay, this is from the earlier lecture that we had the last time, right? So we know how to construct an over approximation n hat of a DNN, right? For checking properties of this form. Okay. Now the question is the following, right? So suppose that n hat is constructed so that n hat for any input x computes a bigger output than what n could compute, right? So this is what we are saying, right? That n hat is bigger than or equal to n hat of x is bigger than or equal to x for every input x. Okay, and suppose that we want to verify the property that n of x is less than equal to c. Okay, then of course, the way we do this is by checking that whether the negation of that is satisfiable or not, right? Now the first question is that what can you conclude about this property holding or not holding? Sorry, I don't know why it got highlighted.
Yeah, normally when you check validity, you check the negation of the property is unsat. Now here, what if it is not unsat, but that if it is sat? Okay, that's the question that's being raised. Sat of the negation of the property. It's
Correct. So if this does not turn out to be unsat, so you know that if it is unsat, then the property holds, right? So you know that if this is unsat, the property holds. But what if this does not turn out to be unsat? What if this turns out to be sat? What can you conclude? Anybody?
So it may or may not be a counterexample. We'll have to check with n because.
yes. Yeah, Madhukar had already covered. Okay, Madhukar, you heard the answer, no?
Correct.
Yeah, and what's your name?
Avik.
Okay, that was Avik. Okay, in this point, Madhukar had already covered. Okay, this relates to, so this could be, certainly it is violating in the over approximation. So he said Madhukar had covered spurious. It could be either spurious or real counterexample. So that's what.
Correct. Okay, yeah. So this is fine. Okay, the second question says, the second part of that question says that. Yeah,
this is important. Okay, that you understand. Yeah, go ahead now to the next question. Yeah.
Okay, so I believe that everyone is okay with that answer. If you're not clear with that answer, or if that does not make sense to you, you should ask a question. Okay. So
You're okay.
Yeah. Okay. So now we are saying that suppose we wish to.
I have raised it, the volume. So can you raise your, can you do something at your end? I think you are, we can hear you, but if you could
sorry,
make it even louder, it will be better.
So I don't know how I can make it louder.
Continue. I will ask our technician to come and see if he can do something here at this end. Okay.
Okay, sure.
Continue.
Yeah. So the second part of that question is that, so suppose we want to verify that the network always computes an output which is bigger than some constant C. Right? So suppose we want to verify that the network always computes an output which is bigger than some constant C. Yeah. Okay, so suppose we wish to verify that the network always computes an output which is bigger than, so this is the property that we want to verify. Okay. Now, the first question is that can you use n hat as constructed above to verify this query? Okay, so what do we mean by that this is valid? So we know that a formula is valid if its negation is not satisfiable, right? So if nx less than equal to c is not satisfiable, right? So this is valid, which means that, nx less than equal to c is not satisfiable. And so nx greater than c is valid if and only if nx less than equal to c is unsat. Okay. Now, can you check this sort of a thing with the abstraction that you have? So the question says that, can you check this sort of a thing with the abstraction that you have in place? Can you do that?
You understood the question, correct? Yeah. So at least there is one answer here by Romit saying, no, you cannot.
Okay, and can you also explain? I mean, give an intuition as to why you cannot do that.
Because n hat is always larger, greater than or equal to n. So, if even if n hat is always above c, you don't know that n will be above c, and if and so that you can't verify the validity question.
Correct. Because of the way you have built this thing, right? So you wanted to. I mean, the reason why we were building an abstraction which generates a bigger input is because we wanted to check whether the input can become bigger by some amount or not, right? So if the property changes, then the same abstraction cannot work in general, right? I mean, it may work in some cases, but in general, you may not be able to use the same abstraction, right? Because the abstraction may be with respect to the property. The abstraction may have been done with respect to the property, right? Because this is a property. I mean, this is a quality of the abstraction, right? So you want in your abstraction that if the abstraction satisfies the property, then the original satisfies the property, right? So this is something that you want in your abstraction, the way you build your abstraction, right? So therefore, because you want this to hold, your abstraction quite often, or in fact, very often ends up becoming guided by the property that you are trying to verify.
Yeah, abstraction is built based on, it's a property sensitive abstraction.
Correct. Yeah. Okay, what about the second one here? What can you conclude about Q holding for N? Q is this property that we wish to check whether it's valid or not. So what can you conclude about Q holding for N if N hat of X less than C is unsat? So if N hat for every input is actually bigger than equal to C, bigger than C.
Yeah. Correct. Yeah, I mean, that is, if it's unsat.
Then can you say something? So the idea is that, if it is unsat, what does it mean? It means that, no matter what input you take, N hat for that input will give you a value bigger than C. Okay. But that cannot tell you in general anything about the value that N will give you for that same input. Because N hat giving bigger than C does not mean much, right? It does not mean anything with respect to. Does that make sense? Is that clear? I think this was also partly answered in the first one.
Yeah.
Okay, but the third one is an interesting thing, right? So what can you conclude about Q holding true for N if N hat less than equal to C is actually satisfiable? What will happen in this case?
Yeah, there's one answer here. Let's see.
Q is not valid.
So if if this is actually satisfiable, which means that n hat is less than or equal to C. So you know that, if the n hat, which is bigger, if that is less than or equal to C, then n will definitely be less than or equal to C. So this is not valid. Okay. So in this case, we know that, this validity does not hold. The validity of this does not.
There is a bug. Okay. So so you could see, yeah.
Correct.
So let's move to 4.
Okay. So the fourth one says that what would be a suitable over approximation n hat of n that can be used for safely verifying properties of this form? Any ideas?
Some n hat which is less than equal to n for every x.
An abstraction which computes a smaller value at the output for every input, which necessarily computes a smaller value, right? Because then you know that if that smaller value itself is bigger, then the bigger value will definitely be bigger.
Here. There's one trick that you can use, though. I mean, as I was making these questions, you can always feed the output. I mean, you could subtract 1 from the output, okay, and then make it negative, and then you will be checking the negation of that by checking less than or equal to. So that's also another quickie. But still, you will have to modify your model somehow to be able to do that. Okay. Yeah.
Correct. Yeah. And that. Yeah. Is there a question?
Okay.
Yeah, sure. And that's also, so you can subtract and do like how Sir was suggesting, but of course you need to know that there is some bound for the output in that case. That the outputs are always between 0 and 1 and such things.
Yeah, I want to skip problem 2, okay, in the interest of time, okay, and then move to problem 3 because that is the crux of it, okay. I'm not sure. I mean, let's not do problem 2. It's just asking if it satisfies these or not, okay? I mean, yeah, so problem 3 is asking you to do that, label all of them minus, plus, and so on. Did you guys do it? Did you have any questions in actually doing it? Because that was what Madhukar explained last week. Were there any doubts there?
So this is which example, sir? Can you?
Oh, you go down. You go down in your thing. No. You already went past it.
This one?
No. Even earlier. The second slide with an example. Go up. This one.
This one?
No,
the middle.
Even earlier. Go up.
No, this is the only.
Oh,
slide.
you are using a different one.
Correct. Okay, let me open the one. Let me open the one that you have uploaded.
Yeah, if they don't have any questions, I think that's okay. Okay. If you go there, then you would get that.
This is the one?
That's the one.
Okay. Sure. So it's here. I've just moved it in the end. That's all. But it's there. Yeah. Okay. So this is the one that we are talking about. Right?
Yes. But although there are no weights there, I'm assuming that there are 1 and minus 1, 1 and minus 1, and so on. Well, I don't know if you want to dwell on this, okay, since we are time. If there are no doubts in the way that ink deck positive negative is constructed, then I will suggest that you go. Or if I haven't worked out the solution, okay, If Madhukar, if you have worked out the solution, you can explain it. Okay. Otherwise, you can move on with whatever that you want to present.
Correct. So I was confused in which example are you talking about, because the slides were different, so I was not sure.
The left side one.
Yeah. Okay. Yeah. So I've not worked it out, but we can do it very quickly, maybe, in just 2 minutes or so.
Yeah, but the only thing is this example does not have weight in it. Okay. So the weights are, I'm assuming that you'll have to have some weights. Okay. I mean, I think it's okay, Madhukar, because
Yeah.
you have already shown an example with the
Yeah.
way it's done. So I think we can move on if there are no questions. Yeah.
Yeah. Sure. Yeah. Okay.
Yeah, I was giving these examples to force them to actually listen to your lecture and work it out. Okay.
Yeah. Which I think is fine. I'll anyway, I'll very quickly.
Is Guhan on the thing? I'm not sure if Guhan is there. Okay. Okay. So if there are no questions, then you can move on. Yeah.
Okay. Sure. So what is it that we were doing in the last class? So we said that we are going to do this this sort of an abstraction refinement. We'll apply an abstraction refinement framework to do this verification of neural networks, and we decided that we'll abstract by merging neurons. And before we could apply merging of neurons on these networks, we said that look, the network in its original form may not be ready for merging. So let me try to bring it into a form which is ready for merging, right? And for that, what we did, we split every neuron into pause, neg, and then again every neuron into increment and decrement. Okay. The idea behind this was to ensure that we are computing a bigger output at the output node for every input. Okay, this was the idea, right? And this is how we actually did this, right? So the positive negative classification can be done by looking at the outgoing edges. It can be done by looking at any neuron in any direction. For the increment decrement classification, we decided that we'll start from the output neuron and go in the backward direction. So we will color this one green, and then every time we go back along a positive weightage, we will retain the color. Every time we will go back along a negative weightage, we'll flip the color from green to red and then from red to green. Okay, this is what we had decided. Okay, and then we further decided that once all this splitting of neurons has been done, we will be merging neurons which are going to have the same marking, so the same positive, negative, and the increment decrement marking. For instance, if you look at these two neurons, they are both green in color, so they are both increment neurons. And they are both positive neurons because they only have positive weight on their outgoing edges. Okay, so we can now merge V1 and V2, and the way to merge V1 and V2 is to create a single neuron, which replaces both V1 and V2. The incoming edge to that neuron, from every neuron in the previous layer, you choose the maximum weight that was coming here. So from X1, the weight that was coming here was 1, and from X2, the weight that was coming here was, from X1, the weight that was coming here was to V1 was 1. And from X1, the weight that was coming to V2 was 4. So you took the maximum of that and you retained 4. Okay. And then on the outgoing side, you sum. Okay. Similarly for X2. For X2 was sending -2 here. And then it was sending -1 here. So you take the bigger one of this, which is -1. Okay, so this is how we are doing the merging of neurons. And I think I left you with an exercise which will show that this indeed creates an abstraction, right? That the value of this, where R denotes value, is actually bigger than the value of this.
Yeah, Madhukar, I noticed that you can, you come through more loudly when you speak into the microphone, I think. Okay.
Okay.
Yeah, that's better.
Yeah. Sure. So I'll try to do it this way. Okay. In fact, is this also fine, or?
Yeah, this is much better. Yeah.
Okay. Sure. Okay. So this is something that we had. This is where we were in the last class when we decided to stop, right? And this is something that I believe you have done. Even if you have not done this, I think it's a worthwhile exercise to go and verify that by doing this sort of a merging, by picking an outgoing edge which is the sum of the weights on the outgoing edges of the earlier neurons that were merged, and by picking the maximum of the incoming for increment merges and the minimum for the decrement merges, like how we had seen on the previous slide, we take max of incoming in case of increment merges and the min of incoming in case of decrement merges. So by taking this, you'll actually have an abstraction of the kind that we wanted, right? So we'll have an abstraction where the output will always compute a bigger value than what it was computing earlier, right? So you can go back and verify this thing. Another thing to note here is that the abstraction is independent of the order in which it was done, right? So it does not matter if you're going to be merging V1, V2, and V3 eventually all into one neuron. It does not matter whether you merge V1, V2 first and then merge it with V3, or you merge V2, V3 first and then merge it with V1, right? So this would not matter. Why? Because on one side, you're going to just sum all the outgoing edges. So clearly that does not matter. And on the other side, you're going to take maximum, right? So you can take pairwise maximum, sorry. Yeah. So on one side, you're going to take the sum, which will definitely not matter. On the other side, you're going to take the maximum. Now you decide pairwise maximum and then compare it with the next one and the next one. It's going to give you the maximum eventually, right? So on both sides, it would not matter, and therefore the abstraction is independent of the order in which it was done. Okay. So this is as far as the abstraction is concerned, right? So I've told you how we can create an abstraction. So the abstraction is going to be created by merging of a neuron, and I've told you, how you can, when you merge neurons, how do you rewrite the edges? Okay, because how can you'll have to remove certain edges and reassign weights to the remaining edges and so on, right? So this is how you do the rewriting, but it's still not clear, what kind of an abstraction you do, right? So although it'll come later, but one suggestion is that you go ahead and merge as much as you can, merge as much as possible. What does it mean? It means that, remember that there are two conditions that we have for merging, right? So we are going to merge two neurons if they are going to be in the same layer. We are not going to merge one neuron in this layer with another neuron in a different layer. We are not going to do this kind of a merge, no. Okay, so we are only going to do merges of the other kind. Okay, so we are only going to do merge of this kind, right? So we are only going to merge these two neurons if they are in the same layer. And in addition that, they have to agree on all these markings, right? On the positive, negative, and increment, decrement marking, right? So they have to agree on this thing. Now, what can you do, right? So given that, you can have four kinds of neurons in any layer, right? So you can have positive increment neurons, positive decrement neurons, you have negative increment neurons, and negative decrement neurons. So you have these four kind of neurons. So what will happen? You go on merging as much as possible. Of course, the order in which you merge is important, right? Because I is not important, as I said, right? The order in which you merge for the final merge, it is not important, right? So you can go ahead and merge, pick any two, merge that with the third one, with the fourth one, and so on. And in the end, you will be left with just one positive increment neuron, like in this case, right? So you're left with just one positive increment neuron, which is the merge of the whole thing, right? And you'll be left with one negative positive decrement neuron and one negative increment neuron and one negative decrement neuron. So if you merge as much as you can, you're going to be left with at most these four neurons in any layer, right? So your DNN could have looked very big. You could have many input neurons and then neurons with 50, 100, 700, 500, whatever. And then there were some output neurons, and now you have merged this into one. So this is 4 neurons, this is 4 neurons, this is 4 neurons, this is 4 neurons, 4 neurons, right? So you have actually made the network much smaller. Okay, but every time you make the network smaller, you also increase the output, right? You also take this farther from the actual output, right? Because of all this, because of adding the effect and then multiplying this with the biggest one on both sides and so on, right? So you take, instead of this 1 and 4, it's like 4 and 4. So that brings, some over approximation. And then you go on doing this repeatedly, which brings a lot of over approximation into the picture, right? So this is, so the network becomes, very, very small, but it also becomes very over approximate in some sense, right? And this is true about any abstraction in general. The more details you get rid of, it will become a coarser approximation, right? It will become the abstraction will become really coarse, right? And if you bring back all the details, then it will not be an over approximation, right? So there is really a trade-off between the the size that you want, which you will be able to verify successfully, which you believe you will be able to verify successfully, and the kind of details that you want in your system, right? So you can get rid of everything, or as much as possible, but then that will leave you with a really over approximate system, which may not be very useful. Okay, if you don't get rid of anything, your system will be very precise, but your verification queries may not succeed. All right. So there is always trade-off, and then this is the balance that one has to arrive at. Of course, it is very difficult to arrive at this balance in general. So what helps you is a refinement strategy, which in some sense assures you that, look, you do your, you go ahead and merge, you go ahead and merge as much as you can. You go ahead and merge as much as you can. Sometime, if you have made it very coarse, then you will, there will be a feedback loop which can tell you how to refine, or that there is a need to refine. Okay, so this is the idea. The refinement loop here, it tries to give you that balance. It's not possible to arrive at that balance in one go, right? Because you don't know what is the right level of details and what is the right size which we will be able to verify. Okay, so the abstraction gives you a technique to reduce and get an over approximation, right? But refinement, tries to get to the right abstraction or the right over approximation, which can be verified and is also, good enough for establishing the property. Okay, so this is the idea. Now let's look at refinement in this particular case. Okay. Okay, so the need to refine comes because the abstraction can become too coarse. Okay. For example, if assume that your network computes the output as 3 for some input, and the property that you're trying to check is that the network computes a value less than equal to 6. Even if the property holds, if you have created a very coarse abstraction, then you may have increased this 3 to something much bigger than this 6, right? You may have increased this 3 to 8. And now you will get a counterexample which says that, if you get, now this x0 itself will be a spurious counterexample. Okay, why is it a spurious counterexample? It's a spurious counterexample because n bar of x0, that abstraction gives it a value of 8, okay, which violates the property, but the concrete gives it a value of 3, which satisfies the property. Okay, so therefore this is a counterexample, but a spurious counterexample because it's not real. In the concrete case, it is not a counterexample. Okay, in the abstract case, it is a counterexample, right? Because the abstraction gives it a value of 8, but you had to prove that it will always be less than or equal to 6, which is actually true for this case, but you are not able to prove it, right? Because you have a really coarse abstraction. Okay, so this explains that we'll have to refine, right? So what do you do in this case? Then you refine your n bar into an n bar prime such that your n bar prime, while it continues to be bigger than the original, it should be smaller than the last abstraction that you had. Okay, so you try to find something between the two, right? Remember that you're bound to be bigger than the original, right? Because otherwise you will not be it will not be a sound abstraction, as Sir had mentioned in the question, in the first question, right? That it is a sound abstraction, which means that if you are able to verify the property in the abstract, the property holds in the concrete or in the original, right? So to get a sound abstraction, you are bound to be bigger than the original, right? So this is something that you are bound to be, and this is something that you want to be because this had become too coarse. Okay, so so this is a refinement, right? So when you try to find something in between, this is a refinement. Okay, this is the loop that has to come into place, right? So you can go ahead and do all the merging that you want to do, but if you become too coarse, you will have to refine. Okay, so in this paper, so again, different problems may suggest a different technique to bring back some of the lost details. This paper suggests a very simple thing. It says that you can go ahead and unmerge a merged neuron. Okay, you can unmerge, or you can go back and you can. So suppose you merge these neurons v1, v2, v3. So it may ask you to go back and restore v2 in the original one and have the v1, v3 abstraction as it is. Okay, so this is an unmerged. Okay, so this is the whole idea. We'll get to the details of it, but this is the idea, right? So refine picks a concrete neuron from an abstract neuron, in this case v2, okay, and puts it back into the network. What does it mean to put it back into the network? You restore v2 as it was, and you restore the incoming edges and the outgoing edges as they were, right? And then you also fix the incoming and the outgoing edges for the remaining abstraction, right? So this is, so from one thing, this is what it means to restore, right? So you create a separate node for v2 as it was in the original network, and then you have an abstraction for v1, v3. Okay, remember that because the abstraction was independent of the order in which it was done, after you have removed v3, here you didn't have to worry whether v1, v2 was merged first, or v2, v3 was merged first, or v1, v3 was merged first, right? No matter which one was merged first, you can still take v2 out and create an abstraction for v1, v3, as if v1 and v3 were merged first and v2 was merged with it afterwards, right? You can simply remove it like as if v2 was the one which was merged with the remaining in the end. Okay, you can always do it this way. You can always think of it in this way. Okay, any questions to this point?
Okay, no questions here.
Okay, great. Okay, so now this is, so now we are nearly we have nearly come to the end of this. So okay, so the abstraction, as I said, you can abstract to saturation, which is to say that you will be left with.
Yeah, that point was made.
Yeah.
You understand?
Okay.
Huh? Saturation means it's 4 nodes. Yeah.
Correct. Okay. And then, of course, you can either abstract all the way to saturation, or you can stop at some point, right? And you can decide for yourself what is a good point for you to stop, right? So you can do that. And then it can also be controlled based on certain heuristics, right? So you can decide that, I'll stop, when I see 25 neurons in each layer, or I'll stop if you can already list down some inputs x0, x1, x2, x3, and suppose their values are, in the concrete network, their values are 4, 5, 6, and 7, and you realize that you'll stop if as long as all of these don't increase by more than 3. Okay, you will stop if for any input the abstract network starts computing an output value which is bigger than the original value plus 3 or plus 4 or something, right? So it can be guided by some heuristic, right? So when to stop the abstraction, you can guide it somehow, like, okay. So these are also, in this literature, they are also called as indicator guided abstraction, right? So you have some indicators which tell you when to stop your abstraction. If your abstraction looks like that it is becoming too coarse, you can stop it. One way to identify that it is becoming too coarse is by looking at concrete inputs and checking how much the abstraction value is increasing from the original, right? Okay. Okay. Then another thing that makes a lot of sense is that when you merge neurons, you try to approximate as little as you can. And when you split neurons, you try to restore the maximum amount of information that you can, or reduce the output as much as you can. Okay. So when you try to merge, you try to increase the output as little as you can. So you increase as little as you can. And when you unmerge or when you refine, you decrease the output as much as you can. Okay. This is the idea. Okay. And how can so one way to over approximate the least is to maybe, okay, so suppose that we are merging this neuron and this neuron, right? And this guy is sending, suppose, a weight of 10,000 here and a weight of 1 here, right? After you merge these two, you will, suppose these are increment neurons, so you will take the weight of 10,000 and you will write 10,000 here also, right? So this is a bad merge as compared to this sort of a merge, which is sending, let's say, 4 and 4.1. Okay, because what will happen if you merge these two neurons, you will make this also a 4.1. Okay, which is not very far away from 4. Okay, so these are the kind of heuristics that they put in place. That when you are merging, you should try to merge two neurons such that their difference in weights is not too much. If their difference in weights is too much, then you will end up making a very coarse approximation. If their difference in weights is not too much, if the difference between these incoming weights, right? And remember that there's not just one neuron which is sending edges here, right? There's a whole bunch of neurons in this layer which is sending edges here, right? So you have to design your heuristic in a careful way. But the whole idea is exactly this. Okay. So I'll just take you over this, right? So these are the merging heuristics, which says that you take the maximal value of A minus B over all incoming edges with weights A and B. Okay. And if that difference is minimal, then you merge. Why do you merge? This is exactly the example that I had shown you earlier. Why do you merge in this case? Because the new edge is closest to the replaced one, right? And every merge reduces a neuron, so you reduce the size anyway. Okay. So this simply says that the difference between incoming edges from every neuron. So suppose these two neurons are being merged, the difference between these weights should be should be minimal. Okay, but what we are saying is that, look, this is not just the only neuron, right? There is also this neuron which is sending here. So you again have a difference, and then for this one also you have a difference, right? So the point is that the largest value of this difference is as small as possible. Okay, this is the heuristic that they use. Remember that you can, even if you replace this heuristic by some other heuristic, you're still going to have a sound over approximation, right? The soundness of this over approximation is guaranteed by the design of this framework, right? The design of this framework guarantees you a sound over approximation. Okay, these heuristics are to ensure that you can be precise as much as possible. Okay, this is not for the soundness. Okay, it doesn't matter. You can merge this 4 with this 1 or this 2 with this minus whatever. You can choose to merge V1, V2 or V2, V3. You may simply ignore the incoming edges. Okay, it does not.
Here. See, if you go to saturation, it all doesn't matter. Okay, if you want to go before saturation, if you don't want to saturate all the way to 4, then it matters which subset of neurons that you pick to merge. Then these heuristics will become relevant because yeah. So these
correct.
Yes. Okay. Yeah.
Okay. Yeah. Okay, and you can try it for this example. I'll update the slides with this link, and I think this example is anyway there in the earlier slide also. So you just compute the difference and find out the maximal difference, and then you decide that, okay, you'll merge V1 and V3 first. Okay, because the maximal difference is the smallest in that case. Okay. Similarly for splitting, right? So for splitting also you have this heuristic, okay, which is guided by two things, right? So you are deciding which one to split, right? So you have merged a bunch of neurons and you're deciding which one to split. Okay. Now which one to split can be guided by a bunch of things, right?
By which one to split? I hope you understand. By which one to split, you mean which concrete neuron that you want to remove from that group and then put it back. Okay.
Correct. So it's actually this step of coming from this kind of an abstraction to this kind of an abstraction plus this original concrete neuron. Okay. So the refinement here is simply undoing the merge. Okay. And that can depend on a bunch of heuristics, right? And again, the heuristics are not important. Okay. The framework remains sound, even without these heuristics or even with a different set of heuristics. The heuristics are not very important here. Okay. So you can play with different heuristics and you can see what works the best for your examples or for your data, right? The heuristics are not important, but what is important is that, this gives you a sound framework. Okay. So the way they do it is that they look at two things. Remember that the abstraction, how we had seen earlier, right? That the need to refine was visible from a counter example, right? Because we had a counter example which
I just have a point here. I mean, heuristics is important in the sense, of course, it is not important from a soundness point of view.
correct.
Define it. You want to pick that neuron which, when split out, will reduce the the precision as little as possible, right?
Correct. Yeah.
Because that's when you make it, keep it still. Okay. I mean, you want to make it as precise. You still, by splitting that one, you want to split that which reduces the precision. I mean, increases the precision as much as possible.
As much as possible. Yeah.
So in that sense, it is important, the heuristics. Okay. From soundness perspective, it is not important.
Correct. Yeah. So for efficiency, of course, you need these heuristics, and for precision, you need these heuristics. And yeah. Okay. So this was, so I was explaining here, and I was talking about this spurious counter example, right? So you can take this spurious counter example, and then you can guide the heuristic, right? So you can decide by splitting which one will you try to reduce this one as much as possible with respect to the spurious counter example, right?
This is an important point. I just want to stress here. So, I mean, this is what makes it counter example guided. Okay.
Yeah.
Which means you use the counter example to guide, to decide which neuron to split. Go ahead. Yeah.
Correct. So earlier, we saw that, for X0, the concrete should have been 3, but the abstract was computing 8, right? So now you check what happens. Okay, what happens when you split the second one? What will it compute for that particular counter example? What happens if you split V1? What will it compute? What happens if you split V2? What will it compute? Okay, and the one that brings you closest to 3, you try and split that. Okay, so suppose if you split V2 and you are computing 6, if you split V3, you're computing 6.5, and if you split V1, you're computing maybe 5.5. So you will try to split V1 so that the network computes 5.5. And for this counter example, you're coming as close to the concrete as possible. Okay.
Is that clear? Yeah. So this can be done fairly easily, because for that particular counter example, you compute what the value is by just simulating the network. Yeah. Okay.
Correct.
No questions here. Yeah.
Correct. So this is exactly what has been explained in this slide. That this for splitting you have a like for merging you had some heuristics. For splitting you have a heuristic, and you can find out, which one to split based on these heuristics. Okay. So I think this is all that I have, except for this last slide, and then get to the. Okay. So one of the things that we had remarked earlier was that, look, we said that, we are only going to be checking post conditions of this form, right? Of checking post condition of the form y greater than c. Okay. Which, I know that there was some confusion earlier that, the property is y less than equal to c, and therefore the condition that you're checking is y greater than c. Okay. I know that, it's difficult to, and sir had actually suggested me to change this. So I've changed it here, just that, in a different slide, I could not change it because you can't just work with one. You need to understand that, the post condition is the negation of the property. So the property is something that you are checking is valid, and therefore you check the satisfiability of the post condition, and therefore it has to be negated. But anyway, without, dwelling on these, let's see that, so suppose you want to check a different post condition for this kind of a network, right? So we said that, we can only check post condition of the form y greater than c. Suppose here you want to check a different post condition. You want to check the post condition that y2 is greater than y1 or y2 is greater than y3, okay? Which is definitely not in the form of y greater than equal to c, right? Which is definitely not in this form, right? The point is that you can actually
Just
add.
one moment, I just want
Yeah.
to make sure this is clear. See, there were two assumptions that were made originally, okay, in considering the abstraction. One, there was only one output in your network, and that your properties were of that limited form. Now, what if you have multiple outputs and they are some arbitrary prepositional combination? Okay, go ahead. Yeah.
Correct. So here, yeah, that's a valid thing. So here there are three outputs, and you want to check a property of, you want to check a post condition of this form. Okay. The point is that, you can change this post condition into a post condition in the desirable form by just adding some more neurons into your network, right? So here is how we can encode it, for instance, right? So you add another neuron here, T1 and T2, and then you try to encode this and this. Okay, so you try to encode y2 minus y1, which is encoded by this neuron here, T1, which encodes y2 minus y1, and then this T2 encodes, y2 minus y3. Okay, and then you want to check that T1, which is max of 0 and y2 minus y1, and T2, which is max of 0, y2. So we have ReLU activation function on these neurons. Okay, and then you have the final output neuron Z1 here, which is which is simply the sum of T1 and T2. Okay, so Z is sum of T1 and T2. Now the claim is that, if I simply check that Z1 is greater than 0, this is exactly the same as checking this original post condition, that y2 is bigger than y1 or y2 is bigger than y3. Why? Because Z1 will be bigger than 0 if and only if either T1 is bigger than 0 or T2 is bigger than 0, right? There's no way Z1 will become 0 if none of these hold, right? So for Z1 to be bigger than 0, T1 has to be bigger than 0 or T2 has to be bigger than 0, okay? And T1 will be bigger than 0 if y2 is bigger than y1, and T2 will be bigger than 0 if y2 is bigger than y2. There's no other way for T1 and T2 to be bigger than 0, right? So, okay, so this is a very simple example, but the idea is the same, that, even if the post condition looks a little different, you should look for ways in which you can encode the post condition into one which is the prescribed format for your technique, right? And it may be doable in more often than not. I mean, it's not, we're not claiming here that this is always doable. We're just saying that, look, it may be doable in some cases, even if it doesn't look that way in the beginning.
But here I pose a question. I claim, okay, I'd like to be proved wrong. Okay, so I claim. So the question that I'm raising, before I say what I claim, can you encode, okay, using ReLU, non-ReLU as a DNN, any Boolean combination, propositional combinations of linear inequalities involving a whole bunch of here, Madhukar showed one, a disjunction of two inequalities, okay? So I ask the question, given a certain number of variables, y1 through yn. Okay. And then suppose I want to express some arbitrary Boolean combinations using not, or, and. Okay, linear inequalities. Can you always encode them in the form using as a DNN, okay, with or without ReLU? Okay, you can use ReLU if you wish. You know, in this case, you see there are some layers which uses ReLU and some layers which don't use ReLU. I claim that it is possible, okay, but it would be interesting to actually show that it is indeed either possible or not possible. Okay, that I might actually give you as an exercise, you know, for you to look at. One hint is you should be able to first encode the propositional connectives, okay, and, or, and not. And after that, linear inequalities. Linear equalities you can always encode, okay, in DNN. Linear inequalities, I claim you can also encode by the way it was, you know, given here, you know, through these things. So I think it should be possible, but I'm not sure if there is a proof that it is indeed possible. But that is an interesting problem for you to think about, and then see if it is doable. Yeah.
Certainly. So that makes a lot of sense. So you should be able to encode these Boolean operators, and then you know, multiplying these variables by constants can be done by, you know.
Yeah. There was also, if Diganta, are you there?
Yeah, I'm here. I have a slightly
early on, Diganta, in one of his thing, you had a universality theorem, correct, Diganta?
Yes.
Now, does that subsume this question that I raised?
No, because not necessarily. It is at least not very directly that I can see, because that theorem was about approximation. So it would only I would only say that, okay, like this particular DNN approximates this given function up to some epsilon, and then it would talk about bounds on epsilons and so it might be possible.
That is for any real function, right?
Yeah, any real to real function.
Yeah,
in fact, RM to RM function.
Yes. So here I'm posing a more restricted problem. Okay, this is just a logical problem. Okay, so you have a formula. Okay, it's an arbitrary Boolean combination of linear inequalities. In some sense, it's a restricted function, a set of functions. Okay, so I mean that's as a separate thing. Okay, so why don't you? I think you should discuss a little bit about the experiments.
Correct. Yeah. I have slides.
Because there were some questions by Romit and other people as to, you know, that this is indeed relevant. Okay, that this whole approach is implemented in a tool called Marabou. Okay,
correct. Yeah.
We'll be using. Okay, and that was actually its utility was Marabou was this work was motivated on this example. Okay, and you know, I'd like you to you know, hear a little bit about this example. This is a fairly large example, okay, and on which it was used successfully, and that doesn't work on Z3. Just through that example at Z3, it's broke. Okay, it did work this abstraction technique. So indeed, there is some value in this reduction that it poses. Yeah.
Yeah. So in this case, you know, there were 45 DNNs that were trained for ACAS benchmarks. So basically, this is an airborne collision avoidance system, which airborne collision avoidance system, which I had spoken about, you know, in the beginning slides. Okay, so this was to decide with, you know, how an aircraft should change directions depending on other intruder aircrafts, right? So the input is a set of sensor readings. So I think there are about 6 inputs. So basically 6 or 7 neurons in the input layer, and then 6 layers of 50 neurons each. So this is about 5 neurons in the input layer, then 6 layers of 50 neurons each, and then 5 neurons in the output layer. So these are sensor inputs to tell you, you know, what intruder aircraft where and at what distance, what angle, and so on. And these 5 output neurons were these 5 output neurons were to tell you the direction should you continue to move in your
So,
current
which
direction
means
or
each,
move right or
so
yeah.
each of these 45 DNNs had a few hundred, like 300 to 400 neurons, correct?
Correct. So they had 310 neurons to be precise, 300 from these 6 layers and 5 input and 5 output neurons. So 310 neurons. Okay. Now this was split across 6 hidden layers. And remember that, they went, by doing this split, the increment, decrement, and the positive, negative split, this could in principle go all the way up to 1200 neurons, because every neuron could in principle be, could in the worst case be have to split, right? We may have to split every neuron. Okay. So this is okay. And they claim that, they could prove it. So instead of this 310, after the abstraction, they could prove most of the properties that we are trying to prove at an average of 269 nodes, right? So this was a reduction. For every property, they didn't need the 310 neurons. They could actually do it at 269 neurons.
Wait a minute. The 269 is a reduction from 1200, nah?
It's actually a reduction from 1200, but we are only comparing it to 310 because you could try to prove the original property on this 310.
No, but in that case, they could have, since the reduction is so small, could they have not proved just using the original on the original network itself?
Correct. So there are 2 claims here. The first claim is that, there is a reduction, no matter how small, but there is a reduction. And remember that, this problem is exponential in the size of neurons. So a reduction by even a small amount is this small amount is in the exponent. So that's actually a good reduction. The second point is that, because of this split of neurons, the edges also got split, right? Because there was an outgoing edge here and there was an outgoing. So in general, the network became simpler in some sense, right? Because not every connection was there from every neuron, because the edges had to be split across. On the outgoing side, the edges had to be split, right? So therefore, these networks were actually simpler. So even though, this could be verified with an abstract network of size 269, this network was simpler than what an original network of size 269 could have looked like.
Simpler in the sense of the formula, that it was the function.
Correct. Simpler in the sense of the computation that it was doing.
No, but the question is, I made a wild claim, which without knowing, is it correct or not, is the question that I asked. I kind of said that without this node merging abstraction, if you just threw the original ACAS network.
So it could not do it. No, it could not do.
It could not. Oh, okay.
Yeah.
So it's still valid. Okay.
Yeah. It could not do, or it could do with a very high timeout limit, but this could do it much better.
Okay.
And in some cases, for different kind of properties, they actually say that, look, they could verify it. From 310, notice that they went all the way up to 1200, and then they came to 385. So in some cases, they verified the same property that they could not verify for this size. They verified it for an even bigger size. But remember that this abstract network was simpler, as I just argued, right? So even though the network size increased in some cases, okay, this could be verified because the abstract network was simpler. So there is some benefit in this abstraction refinement, even though this starts with an overhead of 4 times the split. Okay, so that's one thing. So this was for one kind of properties. They also looked at another kind of properties called adversarial robustness properties. The focus of this talk was to not worry about adversarial robustness properties, but these are very interesting properties to look at. And one of us can cover it sometime, or you can look at this paper and look at the experimental results for this property. There was an even further reduction for this kind of properties. Okay. Yeah, so I think that's all that I have. So we saw that pre-processing DNNs can be very helpful. And by pre-processing, I mean marking of neurons, like how they were marked here. And this is not the only merging that has been looked at. So in this paper, we looked at some way of merging, but this is not the only merging that has been looked at. There's also a different merging that people have explored. And in principle, it's also possible to combine this sort of a merging, the one that we looked at, where we are merging neurons, with a more semantic merging. But, I mean, if there is interest, I can give this paper to one of you and you can look at it and maybe present if there's time. But this is a good area for exploring problems and doing research, because there are different techniques that people are using. These are all fairly recent techniques, but they have not, I mean, this is still far from maturity. So there are still interesting problems to solve in this direction. So you may be interested in exploring this. I can give you pointers. You can send me an email and I'll give you pointers to this paper and other things. Yeah. So that's all that I had.
So any questions? Just a minute.
Hello.
Yeah.
Sulagna this side.
Yeah. Sulagna, tell me.
So at the last, you just briefly covered that point of merging based on semantic similarity. So
Correct.
semantic similarity search we have studied in natural language processing. I was just wondering, like, how it is implemented there in this case. Semantic
Correct. So okay, so I'll tell you briefly how this has been done. So suppose you look at a network, right?
No, firstly,
yeah.
just before you get into a semantic, do you understand why semantic versus structural? So the abstraction that the node merging that was happening here was purely kind of structural. Okay, so you can have a semantic criteria. Okay, go ahead now, Madhukar. Yeah, I just wanted that the rest understood semantic versus structural. Okay.
Yeah, certainly. Yeah. So here, so by semantic here, I mean that, so suppose you have a network and you're trying to merge two neurons. So let's say that, you're still restricted to some layer and you're trying to merge neurons in this layer, right? So which two neurons are the most harmless to merge? So suppose I tell you that no matter what input you give, this neuron always gets the value V and this neuron also always gets the value V. Then I claim that it's okay to have just one neuron and not have two, right? Why have two copies of the same value, right? It does not make sense. Whatever computation you're trying to do from here, you could move all this computation here and then have just one thing, right? So it does not make sense to have two neurons in the same layer which always have the same value for every input, right? So the claim is that if there is such a case that two neurons get the same value for every input, then we can get rid of one of them or merge two of them, whichever way you look at it, right? This is the general idea. Now, what they say is that, look, same value for every input is too much to ask for, right? So they say that, okay, let me relax this a little bit. Let me say that, okay, not the same value, but, close enough values for every input. Okay. And they further relax it. They say that, okay, not for every input, but let's say for, some 1,000 inputs that we have selected. Okay. So if for these 1,000 inputs, these two neurons are getting this close enough value, then let me just keep one of them. Okay. This is the kind of semantic similarity that has been explored, and you keep only one of the two neurons.
I mean, what was the connection to natural language processing, that you?
Yeah, I mean, as I was saying that time, it was like semantic similarity we search when suppose we are having a corpus, suppose we are extracting the vocabularies and there, suppose to say we have to find the value, find the meaning of a word, which we right now we don't have the knowledge of that particular word. So we have to get an idea about the word by the context and also I have some words which have which is of similar meaning, maybe synonymous, but we are not sure about it. So Yeah, I only know the semantics in term of vocabulary and language corpus. So I was really not sure how is it related when it is implemented in this way.
Okay, did you understand? I mean, what I guess what she's saying is could be characterized as the inputs. No, I mean, if certain outputs of certain nodes, if I understand you correctly, they are somewhat similar for certain kinds of input words. Yeah, the neuron output. Can you then try and use merging for those subsets of inputs? Yeah, I thought that might be similar to that for some subsets of inputs.
Yeah. So, sir, how are we choosing that 1,000 many from the
Yeah, so it's not very clear. You pick some inputs, depending on your domain, you pick,
random
certain
sample?
representative inputs for that domain.
Okay, okay, all right. So I was
Okay.
just thinking like we are doing some bootstrap kind of thing, and then like we have n number of that samples, and whether we are getting for each of the n we are getting 1,000 many, and we are coming to a what to say common conclusion from all those. So I was thinking of something of that sort. I was not very sure about what we meant by this 1,000 many neurons select 1,000 many neurons selected, and then this merging is
Yeah. So basically, you want to assess that these two, the ones that you are merging, are actually computing the same value every time. Now, every time is very difficult to check, right? So you want to somehow represent all possible times by a finite number of inputs, right? So whatever represents your domain, that's what is meant here.
okay. All right. Okay,
Yeah.
so thank you.
Okay. Anything else?
Yeah, today I want to go till 5:30. Okay, so I'm missing the shuttle. I mean, I'll take the 6 o'clock shuttle because if any further questions, so I ask for your consideration and cooperation. I mean, if you have other plans, you could. I'm not going to hold you here. Firstly, before just after, having made that announcement, okay, I'm indulging, your cooperation. Any questions so far on this part of the presentation? Okay, anything more that you want to add, Madhukar?
No, I think this is fine.
Yeah, the reason I want to take a little bit of extra time is because Diganta has a few ideas to add regarding some construction of this kind of merging abstractions, some ideas that goes beyond the structural thing. Now, whether he would characterize the ideas that he is going to briefly describe here as semantic or not, I leave it to him. Diganta, okay, so I will make you co-host, and as I said, 5:30, okay, is the limit. Yeah, I mean, I can go till 6. I'll be here because my shuttle is only at 6 p.m. But 5:30 should be good.
Yeah, definitely.
Yeah. So you want to take like 5-minute break? Yeah, no. But generally, I'm saying give people here a couple of minutes. Yeah.
Yeah, sure. Yeah, so I mean, I guess in those couple of minutes, I'll just say that I'm not going to start my video because unfortunately my network connection seems to be a little unstable. So I'm not going to risk
So you're only
stressing the
going to
bandwidth.
describe in words. You're not going to show anything.
No, I'm going to share screen, but I'm not going to show my my video as in the camera feed, the face and the
I
webcam.
wasn't expecting a video. Okay. So anyway, I'll
Yeah,
make you.
No.
You can share whatever that you wish to do. Yeah.
Yeah. So do let me know when I can start. So I guess I'll share screen and get ready.
I want it to be
Whenever.
recorded.
Yeah.
Yeah, that question you had about um, representing any logical, any inequalities as any logical connection of inequalities as um, sort of in the output of a DNN. I think we can only do one level of connectives, as in we can't, like we can only do either a conjunction or a disjunction, but not a conjunction of disjunctions or something like that, as far as I can tell. So we have inequalities. Can you do a knot? I couldn't do a knot. So because the or the and, sort of the constraint that we choose, a larger, greater than, or a less than constraint, that is based on the connective that we choose. And we can only have one of those.
Diganta, hey Madhukar, can you, I think you can, yeah, if you want to, yeah, you have already stopped sharing. I made Diganta also a co-host. So
Yeah.
Diganta, you should try sharing
Yeah,
some.
I'll try sharing.
Works. I don't know if
Yeah.
Madhukar has to relinquish his privilege of being a co-host before you
I
can share.
know.
Oh,
No,
no, actually, it's only
not
me
because.
who can do that. Okay.
Yeah.
Yeah, that's okay.
So I mean, is my screen visible by the way?
Yeah.
Yes.
Yeah.
Okay.
So this is not what I'm going to talk about right now. This is some
No, I think
separate
we
set
have
of
just
slides that I have open.
Okay, now
Yeah.
I'm just going to step out and step in. But anybody, Romit, I'm giving the mic to Romit, and he has some insight into the problem that I raised, and you guys are welcome to prove or disprove him.
Okay.
Yeah. For the logical connective thing. Yeah. So the and or, like the final proposition that the final connective that we have for the whole system, that seems to determine whether we take a max or a min of the whole DNN. So whether the what is it called? Yeah. Whether the relaxation is towards the greater than or the less than side, that depends on whether it's an or an and. So since we can only do, like, since the relaxation is only in one direction, we can only have one final connective, I think. Because so for all the inequalities, we can have nodes. But then, so to connect them, so suppose we have some and we want to take the or, then so we just we take positive edges. And
so you're saying that, okay, so we have some nodes. I mean, yeah, sure. So let's have this discussion again. So we have some nodes which somehow represent some inequalities, right?
yeah, right. And
Yeah, and how exactly is it? So in the sense that the value of this node is going to be, so the inequality is satisfied, what happens to the value of the node coming out of this node, and what happens to the value of the node when the inequality is not satisfied? So what is the encoding that you use, like the sort of encoding convention that you're going by?
so if you have these inequalities, then an or would be, so we take one for every edge to the final node.
So yeah, but even before that, just to make sure that we are both sort of on the same page, the encoding of the inequality is exactly the same that was being proposed by Madhukar sir in his presentation, right? That if the inequality is not satisfied, then we'll have some greater than zero value coming out of this node.
Right.
That sort of a thing, right?
so the linear combination is greater than 0. So we take the
Right.
max.
So yeah, if it is satisfied, then this sort of a thing with one on every edge sort of gives you odd of two inequalities, right?
Right. And for
Yes.
and wait, an and is possible. Mm, So I think for and what you have to do is you have to change the whole parameter. As in for negation, uh, 1 minus on a node. Can't do 1 minus. Right. Yeah. So minus that, and then you have to bias it. But we're not allowing bias. Sure. Okay. Fine. Mm, right. So if biasing is allowed, then I think negation we can do 1 minus. But if biasing is not,
So let's think about this at another time. So, Diganta, you can go ahead. Yeah.
Yeah. So I'll start, but I think
But I
just
think
because
there's
we
a
are having the
hard stop
discussion,
at 5:30. Okay. Hard stop at 5:30,
Yeah.
and yeah.
Yeah. But I mean, just for like one brief minute, I think I mean, I'll make a claim that it should be possible to do all possible linear combinations, and I think maybe one slightly easy way to look at why that should be possible without going into details of how you can do it is to just look at it in a sort of geometric way, right? Like all possible linear combinations of inequalities, Boolean combinations of inequalities is basically disjunction of polytopes. And then the question is that, okay, can disjunction of polytopes be something that a neural network can represent, right? A ReLU can that represent a disjunction of polytopes, right? And the answer to that should be yes. And yeah, so without going into more detail than that, unless maybe after 5:30 we can discuss more about that. But I think it should be possible.
Linear inequalities is just is representable. Okay. So
Yeah.
disjunction of inequalities, disjunction of conjunction of inequalities is a disjunction of polytopes. And you're saying you could represent that. Why? How?
Yeah, because suppose we have some, some polytope like this here and another polytope like this here, right? Then finally what we want is a DNN whose value should be, let's say, greater than some constant C inside these things and less than some constant C outside these, right? So such a DNN, I mean, this is not a real proof. It's just some visual intuition. But such a DNN should be constructible from sort of piecewise linear parts, right? So if I have a function that is, let's say, linear in all of these pieces and sort of peaks over here, maybe I should draw that in some 3D way, right? So I have some function which peaks like this, right? And maybe this is another piece of your polytope, and let's say that's a triangle, and here also we have another peak, and then maybe this function is everywhere else, outside of everything. It's always less than this particular level that we have chosen, this level C, right? So yeah, and this plane sort of, let's say, represents my level C. where this black line sort of intersect these two peaks, right? So then the question is, can we have a function, can we have a surface that looks like, that is say flat everywhere else and looks like these two peaks, right? If we can have such a surface, then as a ReLU DNN, then we have this DNN which is greater than C inside these polytopes and less than C outside, right? And that should be possible because ReLU DNNs should in general be able to represent any piecewise linear function. So precisely that is. So from that sort of an intuition, I think it should be possible. Now, of course, this is not really a proof. This is just some visual intuition. But I think maybe this is a direction in which one can think and formalize and get a rigorous proof of this.
Yeah. Okay. So I want us to move on. Okay, because it's just this is a theoretical problem. So it's not. Interesting. So what I think Diganta, from what I understand that you will be describing is a way of maybe, I mean, improving on the abstraction construction for node merging. Okay, one way. Go ahead.
Yeah. So I'll talk a little bit about I'll talk a little bit about some of the things that regarding this node merging thing. So let's take a sort of slight motivating example. Right, and so like Madhugas has said, I mean, Madhugas said this sort of a framework is actually very general. It lets you do a lot of exploration in terms of what kind of heuristics you want. And as long as you maintain some rules of this framework, you know that whatever you're doing, whatever merges that you're doing, it is at the end of the day going to always be sound. So you're not going to introduce some unsoundness or get a wrong proof somewhere. So as long as that is the case, you have a lot of room to explore a lot of heuristics and get more and more better precision. And, you know, as an example, one of the things that he was talking about in terms of heuristics that you could look at is this similarity, right? So, so in general, there is a really interesting line of thought and a research direction in which one can look at things. I at least feel, but to motivate the particular way in which, like some of people here are looking at this particular problem. We have this particular DNN, let's say, where we have 100 and 100 in these nodes, and 1 over here, 1 and 1 here, and 2 over here, right? So in this sort of a situation, here is a question. So is this DNN actually redundant, right? So one of the, you know, points that Madhugar mentioned was that, you know, okay, we have a situation where if two nodes are always seeing the exact same input, they're redundant, that you can sort of get rid of one of them or merge both of them into one, whichever way you want to look at it, right? Now, my question is that is something like that happening here as well, right? Of course, it's not the case that these two nodes, and just for, so both of these two nodes are actually increasing, and both of them are also actually positive, right?
Okay, just a comment. I mean, if you could write it a little bit bigger, at least the numbers.
Oh, yes. Sorry. So I am, yeah.
Oh, I have to move
Yeah.
the screen. Yeah. Oh, he did it. Yeah, I can make it full screen here. It's much better now. There. I don't know. I mean, this.
Yeah. Oh, no, I'll keep things much bigger.
Okay. Better now.
Yeah.
Okay. Go ahead.
Yeah. So the same question can be asked over here as well, right? In the sense that, you know, okay, is it the case that these two nodes are equivalent? Of course. Okay. So, you know, first of all, both of them are ink, both of them are positive. So pos, but they are not equivalent in the sense that, they're not redundant in the sense that they don't really see the same values, right? It's definitely not the case that both of them see the same value, right? But are they still redundant in some way, right? So it turns out that this network. So actually, you know what? Do you have any idea? Like, do you think that these two nodes are redundant? Is there actually a way to somewhat, in some way, get rid of one of the nodes and change the weights and biases of the network so that the network's behavior does not change?
Yes, you can remove the second node and scale the first one's outgoing weight by 2 by 101. Do 1 plus
Exactly, right?
2 by 100.
Yeah. So this is actually exactly equivalent to sort of this network where we have, you know, 100 and 100 coming here, and let's say this will be what, 1.02, right?
Not 101.
This one here.
Yeah, no, this is fine.
Yeah. So yeah. In fact, this is exactly equivalent, right? So that is correct. So this it turns out that there is some redundancy in this network, right? And it was kind of not you know, the kind of redundancy where the inputs are exactly equal, but something else is going on, right? Now, one can think of this problem in some generality, in the sense that, you know, if you were to pass this problem to this particular way of doing a merge, which is that you'll take a max and then sum of the outgoing weights, that would give you a network that looks something like this, right? Where because you're doing a max, you take 100 and 100, but then because you're doing sum, you take 3, right? So clearly this network is highly over approximate. I mean, this is not a good sort of approximation at all, right? It is going to introduce a lot of spurious counterexamples potentially if you try to verify with this, right? Whereas there is actually a network where you can get rid of one node. So this network is of the same size and really the similar complexity. But this network behaves exactly the same as the original one, right? So in some ways, you can think of this network as being the optimum merge in this case, right? And I put optimal in quotes because, you know, whenever we're talking about some kind of optimum, we have to say what is it exactly that we're trying to optimize. So in this case, the amount of over approximation that we're introducing, but then we have to sort of define it in some clear way and so on. But this is in some intuitive sense an optimal merge, right? And then, you know, min max and sum in this case is not giving you an optimal merge, whereas we know that okay, there is a much more optimal merge which, you know, you can sit down and think about and figure out, right? So then this becomes a question: what is the optimal merge? Right? So yeah. So this is in general the sort of thing that we are like think the line along which we're thinking, right? So can we sort of find the optimal merge, right? And this is actually turns out to be in many ways there's a lot of subtleties in this question. Again, I'm not going to too much technical detail beyond this sort of example level of things, but the first question is that is there actually an optimal, right? In the sense that is there a unique map?
There were two parameters that I could think of. Okay, one
Yes.
in that can somewhat define optimality. One is, of course, you want it as small as possible. So,
Right.
number of nodes in your network. I mean, the merge network has to be, in some sense, minimal. The
Right,
other thing is the difference in the outputs
Yes,
of
precisely.
the original
So
and
the
that has to be minimal. Correct?
correct. In fact, that is precisely what we want to mean. We, in fact, in some sense, we want to, given some input domain, we want to minimize the maximum possible output value that we see, right? Within this sort of abstraction refinement framework, because ultimately what we want to prove, is something like this, that says that, okay, the output value is less than equal to some max, right? And then if you do want to prove this, the idea is that whatever we do to the network to change the output values, if the maximal output value doesn't shoot up to more than this upper bound or this max that we have, then we can actually say something about proving this original property, right? So in a definition of optimality that we would like to have, that could work very well, is the maximum value of the network with maximum, where the input varies within some domain, right? So the maximum values of the network should should increase minimally, right? No, of course it's hard because there's a maximum over here. This maximum is a maximum of a network, right? So it's maximum where input varies in some domain, which is usually some sort of an interval of some neural network, right? And this is something that is hard to calculate, right? So practically you can't really talk about this or do anything with this maximum from an algorithm or an implementation point of view. So most likely what the only thing you can do is sort of estimate this maximum, and that is exactly what the sort of definition of optimality that we are thinking of. But of course, there is two things, right? There's this theoretical perfect kind of definition of optimality, which is this maximum, which is going to be exactly what we're looking for, and then there's this estimate. But then there is also another view of optimality, which is that which is this local view of optimality, which is, can we do some change? Can we only look at the immediate weights and biases in each layer and do something, right? And it seems that is at least going to be, although if that were possible, things would be very efficient, that is going to be somewhat hard. But yeah, this is exactly what we're looking at. And the other sort of related question, slightly related question, is that is there some unique thing?
Could I take a guess?
Yeah.
Uh,
Yeah, sure.
We're trying to merge any two nodes, right, in the same layer.
In the same layer, yeah.
Right. So we consider every pair, like every input pair. So example, for the two nodes, for every node in the previous layer, we have an input pair. And if the weights, so if whichever one of those two is the maximum, if that changes as we enumerate all the pairs, then we don't have an optimum, right? But if that doesn't change, we can take the smallest ratio. Yeah, we can take the smallest ratio between the larger one and the smaller one, and then add the output weight in that ratio, weights in that ratio, right?
Okay, so just to understand what you're saying, we have some layer where we have many possible nodes, and then we're trying to merge these two nodes in the next layer, right?
Right.
Yeah. So now you're saying, let's take pairs from here. So let's take this guy and this guy, for example. And then what are we going to do?
No, we take suppose we take the first previous node, and we take the first node in the first layer, and we take.
So let me just number the nodes. So let's say that this is yeah, so this is say that node 1, 2, 3, 4, 5, 6, 7, right? Yeah. So you're saying let's take 1 and then let's take 6 and 7.
So yeah, we consider the 1, 6 and the 1, 7 edge. And we have, say, some ratio of the weights.
Okay.
Okay, for now I'm just considering positive weights.
Sure.
Right. And then so we do this for every previous node, so 2, 6, 2, 7 and 3, 6, 3, 7, etc.
Correct. Yeah.
And we check if the ratio ever moves from greater than 1 to less than 1 or the opposite.
Yeah. Exactly. That is a good idea. In fact, that is that is something that we have. Yeah. So uh, so this is actually really good intuitive idea in the sense that you just look at the ratio of the weights when you're merging these two nodes and then see if this ratio is sort of stable across various choices of these guys, right? And if it is stable, then that is a good guess that these two can be sort of merged, because then you can scale these weights to bring the incoming weights close by correspondingly scaling the outgoing weights, right?
Yeah.
Yeah. So that is a really good idea. So I think so basically that would essentially look something like this, right? So where you're if you were to think about these neurons. So if I look at it from the other point of view, if I were to think of these neurons are making some sort of decision, right? In the sense that there will be a linear expression involving the previous layer values, below which this neuron will be 0, above which it will be non-zero, right? So there is some sort of a decision boundary for each neuron. And what you're really comparing is, are the decision boundaries close for these two neurons, right? Yeah, and this is something that we have you know explored in some sense. And so yeah, so there are a lot of such heuristics that one can in general look at, right? But I guess in the last 5 minutes that I have, I'll just basically talk a little bit about the thing that the sort of framework in which we want to look at. See, in general, each one of these heuristics, they answer two questions, right? So like you're saying that you're going to compare these ratios and then scale the outgoing weights and then add things up, right? So this actually answers two questions. The first question is, which nodes do we want to merge? Right. So in our case, if we had a third node where these ratios were all over the place, I'm assuming say we had some third node pair over here, 7 and 8, for which these ratios were all over the place. So I'm assuming you would then sort of conclude that this is not a good merge to do, right? So this is one question. The other question is, how do we merge them? Right? So if we can sort of answer these two questions, essentially we are done. So any sort of heuristic, any heuristic that you propose, these are essentially the two questions that you're trying to answer, right? And then the sort of high level view is that, okay, now that we know that these are the two questions that we need to answer, can we actually learn the answer to these questions? Right? And this is going to, when I say learn, I mean, learn via something like some sort of a machine learning technique, let's say gradient descent or something like that, right? And then, you have this, you have sort of one learning problem, which if it does converge, it will actually get you somewhere close to the optimal merge, right? Because again, this is something that you propose is a heuristic, right? So yeah, maybe it will work in a lot of cases, but it does, the question does remain that, is this actually the optimal, right? So previously we had a heuristic where we are doing min, max, and sum, and I can come up with an example where it works really well, but as I also showed, one can come up with an example where it does not work. Now we have a new heuristic which you're proposing. Let's look at the ratios, and we can ask the same question: is this actually optimal? Is this the best you can do in all kinds of cases? So if you can argue that you can know this is the optimal,
Ratio
if you,
thing, I was not even
yeah.
sure if it gives you a sound thing. It will.
No,
I mean,
it'll.
I don't know. I mean, I missed some of the details. I mean, the way you describe is a bit sketchy, but as long as
Yeah,
you could make it sound, then it's probably a worthwhile thing to investigate. Yeah. Okay. Yeah. So, but
Yeah, definitely.
use learning techniques, then you will have to somehow, in order to ensure that it is sound, you will have to include those soundness constraints
Yes,
into the
exactly.
optimization objective function, correct? Yeah.
Correct.
Yeah.
Right, exactly. So that becomes then sort of the challenge, right? So if you want to do this, so the benefit of this, these are two things, right? So benefit is that if this does converge, if learning is successful, then what we immediately get is we get something like something that is that we know to be optimal, right? But the challenge, of course, is firstly, how do you pose this as like what is the parameterization? So if say let's say that we want to do gradient descent, right? So how do you parameterize this? How do you encode or parameterize this into a optimization problem, right?
Yes. Specifically gradient descent, huh? Or something else.
Yeah. Or if you want to use some other algorithm, you'll have a similar version of this challenge where
Yeah.
that particular algorithm requires some particular encoding, and then you have to think about how do you frame these two questions within that sort of encoding kind of a environment, right? And then the second sort of challenge is how do you deal with the soundness uh, condition, right? So you just can't just optimize and come up with any answer to these questions. In particular, for number 2, there is a soundness associated with that. So not all possible merges are actually allowed. Only sound merges are allowed, right? This soundness is actually a local property, which is actually something that we have to use, and that is sort of the crucial feature, I would say, of this INCDEC framework, which is that it allows us to reduce soundness to a local property, right? So if you look at what we're doing whenever we're doing min, max, and sum, we're sort of making sure that the value of the node increases for inc nodes and decreases for dec nodes, right? And that is all that we need to make sure. And we need to make sure that holds for that particular neuron. When we're looking at this particular neuron, we don't really worry. We don't need to worry about what happens in the rest of the network. So in that sense, soundness is a local property. But nonetheless, we have to deal with soundness, right? And this becomes the two challenges. And if we can sort of solve these two challenges, then potentially we can reap this particular benefit of learning in optimal merge. And so this is that is sort of, I think 5:30 is already here, so I'll not go further. But this is the sort of framework in which we're looking at things. So yeah. So yeah, sir had a discussion. I think right before class today, sir was talking about some of the things here. So I thought so just wanted to talk very briefly about this because it is related to the INCDEC framework, and it is one of the things that can be one of the directions of thought, I guess you can take this into. So if people are interested, then we can discuss more.
Yeah, this is actually direction in which Diganta, you're looking at. Okay, so if indeed there is interest to you guys to look at, because this is crucial for this kind of verification. Okay, it's all well and good. I mean, tic-tac-toe, I mean, you can do. I mean, they have done ACAS, okay, which is a fairly big thing. But nowadays, these neural networks that are being built, I mean, they're so huge, okay? And I mean, if you go to natural language processing with all these generative AI and so on, I mean, those models have multiple feed-forward networks with lots of complicated, fairly things. So the question is, how do you even scale to those things? So this reduction technique is very important. And therefore, at the core is this thing. And I think Diganta has done some work in using, exploring this optimal emerging thing beyond the simple max sum thing that was done there using gradient descent. So if indeed there is interest, we are not going to be discussing this as one of the papers in the thing, that if as a master's project or project, when you want to get involved in that research, and if that tickles your fancy bone, then you can get in touch. Okay. So do you want to say anything more? I mean, it's 5:30 already.
No. This is all
But,
I had. Yeah.
so that I think this is, I guess this is enough detail for, to maybe tickle their fancy. Okay, so yeah, okay. So any questions that you want to add or have? Yeah. I mean, I hope you understand why we're dwelling so much on this thing, because scaling these verification techniques, we have so far looked at Z3 directly, throwing it at Z3, and then doing something like node merging, the simple node merging, structural node merging. And there are people looking at other ways to merge these things in a semantic way, okay, that maybe gives better precision, for the thing. Maybe like what you're saying, what you were saying about how you do, if they behave certain similarly for certain words in the natural language processing, maybe that is something that you can consider as a semantic merge criteria. I think that's how I understood what you were, Sulagna, that you were bringing. So all. Yeah, I think if Madhukar can send that reference, Madhukar, yeah? Are you still there? Oh, maybe Madhukar is gone. Anyway, I'll get him to, with the thing, and if you're interested. Yeah, if you could, work it out, what your ideas are, flush it out. Yeah. Okay. Thank you, Diganta, and thank you, everybody, for putting up with the thing. Yeah. Okay. No. It's Monday. No, there's no class on Friday. Monday, Thursday. Friday, I'm just reserving as a alternative slot if indeed we'll have to do. This week, this is all it is. But what I have offered, okay, this is a good thing. I mean, see, Shauryam or I'm available for tutorial. Now, I know there is quite a few things on your plate right now, okay? Besides reading up and then deciding on your paper, okay, which is very important. There is also this, 2 assignments that you're working on, okay? Multiple assignments, I guess I put in. So if there are on a demand basis, I'm anytime that you could, ask us, okay, call us for a tutorial, and then we'll come and then answer your questions about issues that you're having with the assignment problems. Okay, that we are already available. You'll have to just drive it. Yeah, the thing. So that. Any other questions? Yeah. Okay. Thank you.
Yeah. Thanks a lot. Bye. Bye.
Part 2, the tic-tac-toe thing, huh?
The recording has stopped.